All right, so this is sort of continuing the question in the last video. Is it possible to start with the solution to a differential equation and reverse engineer the original differential equation? In the last video, I did a separable one, and in this one, I'm going to do a homogeneous one. So let's start with some differential equations solution. So the textbook claims that oops, that's a cosine x, that this is the solution to some homogeneous differential equation. I know that I could take the derivative here, but I know that the differential equation, when it's homogeneous, involves y over x. So I'm going to divide both sides by x only because my goal in this video is to show that we can get back to a homogeneous differential equation. So now I'm going to take the derivative of both sides. And so the derivative of y over x, got to use the quotient rule. So f prime g minus f g prime over g squared. The derivative of negative cosine is sine of x. And so then if I solve this equation for y prime, I get y prime x minus y equals x squared sine of x. So y prime x equals x squared sine of x plus y. Oh, actually, I guess this right here is the original differential equation that they provided in the textbook. So you could leave it there, or just to continue, I could divide by x, and then I'd get y prime equals x sine x plus y over x. And then from there was how we used uh, the substitution of v equals y over x is what we would use to solve that. Um, that was pretty quick and easy. Let's see if that was just kind of a fluke, or if it works just as well with another problem. In a different problem, they claim that you can do y. Um, sorry, the formatting is a little weird on this. Y equals x e to the natural log of 4 plus 1 minus x over x. That's all up in the exponent. So I'm going to try the same thing I did before. Divide by x, take the derivative of both sides. So here we get y prime x minus y over x squared. The derivative of this, an exponential, stays the same, except for you multiply by the derivative of the exponent, which is itself a quotient rule. So that's super. So we're going to do f prime times g minus f times g prime over g squared. Okay, something I noticed right away is you can multiply both sides by x squared and get rid of all that business. What did the original problem even look like? So the original problem looks like xy prime equals y times ln x minus ln y. I don't know if I'm going to be able to make it look like that. Let's try. Y prime x, and then let's add a y over. So it equals y plus e to the natural log of 4 plus 1 minus x over x times negative x. I'm going to distribute the negative. So this cancels out. So where I'm at is y prime x equals y plus e to the natural log of 4 plus 1 minus x over x times negative natural log of 4 minus 1. And what the textbook claims is that this is equal to y prime x equals y times natural log of x minus natural log of y. I don't see any real way that I can make my red expression turn into my blue expression there. Um, Maybe if I remember that the letter y is equal to x e natural log of 4 plus 1 minus x over x. So the natural log of y would be the natural log of this product and when you take the natural log of a product, you can split it into the natural log of the first thing plus the natural log of the second thing. So that would be the natural log of x plus, and then the natural log of the rest of it will cancel out the e, leaving me with natural log of 4 plus 1 minus x over x. So that's what the natural log of y equals. And so I'm wondering, let's see, if I write out, like I guess I wouldn't see starting from the red how to turn it into the purple. But if I knew I needed to turn it into the purple, I could see how taking this expression here and saying take natural log of x minus that natural log of x, because if I do natural log of x minus natural log of y, that's going to get rid of that natural log there. It's going to put a negative on all of this, and then I'm going to multiply it by this here. I can see how we might be able to get back there. So I guess the answer to the question is like you can reverse engineer a solution into some sort of differential equation, but there's not really an obvious route to get back to a particular one that was given to you in the textbook. And it's the same idea. Like if I just tell you the solution to a regular equation is x equals 7, you wouldn't be able to reverse engineer the particular equation that the textbook had in mind. Like knowing that x equals 7 doesn't tell you whether it came from 2x equals 14 or it came from x to the third equals, 343, or the sine of x was equal to, so you don't know what type of equation the solution came from. And I guess it's sort of the same thing here, that given a solution to a differential equation, you don't know what type of equation it necessarily came from. So anyway, comment, ask questions, let me know.